So, bridging fault. So, this models shorts between two circuit nodes. So, so this is another type of physical defect where two lines have been shorted. So, so the effect of this shorting depends on the technology that we have, and also some other factors that is directed by the technology. So, this is bridge fault is not excited unless two circuit nodes have opposing logic value. So, if both the lines are having same logic value, then naturally that is not counted as a fault, both of them being 0, both of them being 1. So, it is not an issue. However, if the lines if the signal values of two lines are different, then which one will persist. So, that becomes the question, and there can be several cases of this bridging. Okay. So, first one is the AND bridging. So, AND bridging is the faulty value is the AND of two involved nodes values. So, if it is AND of two values, then that is one type of bridging. Similarly, OR bridging means that it will be having two values, the OR of them. So, that will come as the new value down the line. So, these are the two cases. Another possibility is the dominance. So, x dominates y. So, value of x will dominate, then x dominates 1 y. So, x dominates y if x is equal to 1. So, so for x equal to 0 it will not dominate, but for x equal to 1 it will dominate. Similarly, x dominant 0 y. So, x will dominate y if x value is equal to 0. So, these are the different types of cases, and actually they have been derived from the physical defects that occur. So, based on that, so these are the different cases that can happen. So, these are the symbolic representation, like in the fault free circuit. So, this x line and y line, so they are running. So, in the faulty circuit, if there is an AND bridging, then what will happen? So, these two values, as if there is an AND gate, and the AND gate output drives the lines x dash and y dash. OR bridging, these values are ORed, and the OR gate output is driving the two lines x dash and y dash. Then x dominant y. So, as if the line y is broken. So, in the fault, so we can model it like this, as if the line y is broken, and there is a fan out coming of line x and feeding the line y dash. Then x dominant 1 y. So, x will dominate over y if x equal to 1. So, this is modeled like this introduction of this OR gate. So, if x equal to 1, then x and y dash, they both of them are 1, but if x equal to 0, then y comes to y dash. So, that dominance is not there. Similarly, x dominant 0 y. So, that is by AND gate. Okay, so, x comes here and this y comes here. The x value is 0, then irrespective of the value of y dash value will be 0. So, as a result, so this is another type of faulty circuit model. So, we can modify the circuit to this faulty circuit model and run some ATPG tool to generate the bridging fault patterns. So, this is modeled as a constraint stuck at ATPG. So, it is like this, a concept. Suppose I am trying to generate a test pattern for AND bridge x y. So, we can do it like this, that detect x equal to y, x stuck at 0 with setting y equal to 0. So, AND bridge y, so x AND bridge of x and y. So, situation was like this, x and y, they were coming and they were going to the line x dash and y dash. So, this was the situation. So, now we detect, so if we detect x stuck at 0 fault with the setting y equal to 0. So, y is made equal to 0, and under that condition we are trying to detect x stuck at 0. So, x stuck at 0, if we want to detect, then we will put a 1 at this point and we will try to see the output here x dash and y dash. So, these two outputs we will like to see. So, if this bridging is not there, then I will get x dash equal to 1 and y dash equal to 0. But if this bridging is there, then this line is also 0. As a result, this AND gate due to this bridging, so this gate will become equal to 0. So, that way it can detect this fault. So, under the constraint y equal to 0. So, if we try to detect x stuck at 0 fault, then we can find a bridging between x and y. Similarly, we can also do this thing by setting x to 0 if we try to detect y stuck at 0 fault. So, that also will find out the bridging between x and y. So, we can do either of them, and by doing that, so we can generate the test pattern for this AND bridging of x and y. So, these conventional stuck-at ATPGs, they can be utilized for they can be modified for these bridging faults. So, like this AND bridging, so for others also I think you can understand what to do. Like for this OR bridging also we have to do this stuck-at one stuck-at type of thing. Similarly, this x dominance y, so so we can put this line to some value, x to some value and y to some value, and we say that we modify the circuit so that this line is coming. So, we just see that under the constraint that this y value is 0. So, are we getting the value of x at the y dash, or similarly at value of y being equal to 1, are we getting the value of x at the y dash. So, the ATPG tool can be modified to put this type of constraints, and we can see the test pattern generated by them for this purpose. Next, we will look into another very important issue in test pattern generation, which is known as test set compaction. So, what happens is that in the testing process, so then ATPG algorithm, so it is initially given a set of faults f. So, f is the set of faults f1, f2 up to say fk, there are k number of faults. Now, the test pattern generator ATPG generates the first test pattern T1. Now, when it generates T1, so it finds out the faults that it can cover. Maybe it covers the faults 1, 5 and 9. Then it generates the fault pattern T2, and it detects some faults. Okay. Now, it may so happen that as we are generating more and more patterns, the new faults that are getting covered by this pattern start decreasing. Maybe T2 detects the faults 1, 5 and 15. So, with the knowledge that T1 has already detected 1 and 5, so we can say that T2 has detected only the fault 15. So, this way the amount of new faults that are detected start decreasing as we are generating more and more patterns. Now, if we want to minimize this number of patterns in the test set, then what is required to be done? We need to select the set of vectors that can detect only that can detect all the faults, but the number of patterns is very small. So, what is done? So, what is required is that we want to reduce the test set size to reduce test data storage and test application time, because this cost of this automated testing equipments or ATE, they depend on the amount of memory it needs and the amount of number of channels that are there, and naturally the test time, if the test set is big, then they need to be stored on bigger storage, and also the transfer time from ATE to chip, so that is also going to be high. So, this test application time increases and test data storage increases, as a result the test cost increases. So, if we can reduce test set size, then these factors will come down. Okay. So, to allow, what we need is to find a minimal set of vectors that can detect every fault, okay, every detectable fault definitely. Now, first, so for this purpose, how do we proceed? First, we build a detection dictionary. So, in a detection dictionary, for every pattern we list down the faults that it can detect. So, say we have got a situation like this, that a ATPG tool, it has given you these 4 patterns V1, V2, V3 and V4, and there are faults F1, F2, F3, F4, F5 and F6. So, these are the 6 faults that are there in the circuit. Now, by doing fault simulation, we find that V1 can detect the faults F1, F3 and F5, V2 can detect F5 and F6, V3 can detect F1, F4 and F6, and V4 can detect F2, F3, F4 and F5. Now, out of these vectors, so if you look carefully, you will see that there is the vector V4 that detects the fault F2, and this fault F2 is not detected by any other pattern. So, if you are looking for a good coverage, then the vector V4 must be included in the set, in the final set of test vectors, vector V4 must be included. That way V4 becomes an essential vector, a vector that detects some faults that no other vector can detect, that is an essential vector. So, we include that essential vector into our test set. So, V4 is included in the test set. After that, we can have some sort of test set covering algorithm to find a minimum test set that every fault is covered. So, set covering algorithm is that we have got a universe U of elements, say U1, E2 up to En, and we have got these individual sets S1, S2, S3, etc., which are actually subsets of this U, subsets of this U. Now, if there may be say k such sets, each Si is a subset of U. Now, the question is that from this S1, S2, etc., so I need to select a minimum set of subsets, minimal set of subsets. Maybe I select S1, S3 and S5 such that all these elements will be covered by that. So, that is basically the set covering problem, but the point is the set covering problem is an NP-hard problem. So, you cannot have an exact solution that will give you the optimum solution and the algorithm will run in polynomial time. That is not going to happen. This is a hard problem, but this here what we have is basically a variant of the set covering problem, where the universe is the set of all faults. Then the subsets are these the faults covered by these individual vectors V1, V2, V3, V4, and the problem is to select the subsets, like select the subsets V1, V2 from this set of V1, V2, V3 and V4, so that all faults are covered. So, the universe has to be covered. Okay. So, if we can do this thing, we can do a test set compaction. Now, sometimes what happens is that the vectors are incompletely specified. So, some vectors, so maybe that as we have seen that in many cases for generating say some test pattern, say if we want to test this line stuck at 1, okay, then it is sufficient to put a 0 here. So, this line can be do not care. So, the test pattern for this stuck at 1 is 0x or x0. So, whatever we do, so they are basically the some so there may be some do not cares. So, if I have got a large circuit, so if I have got a large circuit, then what will happen is for testing the fault, a particular fault, it may require to set only a subset of inputs to some proper values, and the remaining inputs here and here, so they may be left untouched by the test pattern. So, test pattern will keep those bits as do not cares. Okay. So, these do not cares can be used effectively for this compaction purpose. For example, it may so happen that some of these vectors are compatible vectors, means in one vector is suppose say 1 x 0 x and the other vector is x 1 0 0. Then what happens is that if you take, so instead of taking two vectors, so if I just take a single vector which is 1 1 0 0, so what is happening is that 1 1 0 0, so this satisfies the first vector as well as satisfies the second vector. So, instead of taking two vectors, so we can select a single vector, and that is sufficient for getting this for covering both the vectors. Okay. So, faults that are detected by either of these two vectors will be detected by this new vector as well. So, that way we can reduce the size of this test set. So, what we can do, we can have a set of after the ATPG has given me the set of test pattern T consisting of the test set T1, T2 up to say Tn, n test patterns are there. So, and they are having do not cares. Okay. So, this T1, T2, T3 they have got do not cares. So, what so we can view this test pattern set as a graph consisting of these vectors T1, T2, say T1, T2, T3, T4, etc. Then we put an edge between T1 and T2 if they are compatible. So, compatible means for all positions I in T1 and T2, if T1I equal to T2I or T1I equal to do not care or T2I equal to do not care. So, if any of these three cases occur, then we say that if for all positions if this thing happens, then we say that the T1 and T2 they are compatible. So, in this case, so we can replace T1 and T2 by some vector. So, what we do, we construct this graph or we put the edge between the vectors which are compatible. So, it may so happen that this T1 T2 is compatible with T3, T4 and T1. Similarly, T1 is compatible with say T2 and T4. Now, we see that if we if we do a clique partitioning of this graph, then this becomes a clique. Okay. So, in this clique I can, so these three vectors can be replaced by a single vector and this is another vector. So, ultimately I can, if that new vector is say T new, so that is one vector which replaces this T1, T2, T4 by properly some of the x's in them they will get specified. So, T new and T3, that is the new test vector set that I have. So, that has got only 2 vectors in it. Okay. Instead of 4 vectors in the original set, now I have got only 2 vectors in it. So, this way we can have this thing we can have this compatibilities, and accordingly we can reduce the size of the test set. Another way of reducing the test set size is by reverse order simulation. So, what happens is that while we were doing the test pattern generation, the first test pattern that is generated, it is detecting some faults, as I was telling, maybe 1, 5 and 9. T2 is detecting again some faults. So, what in the ATPG process, what we have said is, as soon as one fault is detected by the test set, by a test pattern, so those faults are dropped from the candidate fault list, so that successively that ATPG tool is not bothered about generating test patterns for those faults again. So, what is so if we drop these faults 1, 5 and 9, then this T2 will detect some other faults. So, it may be detecting say 2, 3 and 15, okay, 2, 3, 15, 16. Then maybe T3, so it will detect so T3 will detect faults which are not present in this set, maybe it detects the faults 100 and 101. So, that way this ATPG has been made to cover the faults. Okay. So, it has given me this big set. So, naturally as you go down and down in this list, so last few patterns, so they will detect very few faults, maybe one fault each or something like that. But you see that any pattern say T50, it has detected some faults. So, it has detected the faults say 60 and 70. So, these are 2 faults detected by this set. But the point is that at this point of time, so all these faults that have been detected by the previous pattern, so they have been dropped from the set of faults. Okay. So, this apart from this 60 and 70, this T50 may have the potential to detect some of these previously detected faults as well. So, if you do a fault simulation of T50, you may find that T50 detects not only 60 and 70, but it also detects the faults like 1, 2, 3, 5, 9, 100, 101. So, it may have the potential to detect all these faults. So, what is required is that if we do a fault simulation in the reverse order, then if we include T50 into the set, then this pattern T1 is not required, because it is 159, it is already covered by T50. So, this will go, and similarly T3 having 100 and 101. So, this will also go. So, if we do a reverse order fault simulation, then it may be possible that we can drop some of the previously generated patterns, and we can drop them from our consideration. So, this is what is the reverse order simulation. So, simulate the test set in reverse order, and some vectors may no longer be needed. So, that way also we can reduce the test set. Okay. So, this is the test set compaction. Another important issue with the ATPG is the n detect. So, n detect tells that sometimes it is necessary that we detect every fault n times. So, n may be so by default n is equal to 1. So, once a fault is detected by a test vector, so it is no more considered for test pattern generation by test pattern generation tool. But suppose we make n equal to 2, that means the first time the fault is detected, it is not dropped from the set of candidate faults, but if it is detected by one more pattern, it will get dropped from the set. So, this idea is that detect every fault at least n times. So, n vectors that detect a fault must be different. So, for every fault now I have got n different vectors. So, the fault coverage remains same, but it can enhance the defect coverage. So, defect coverage why? because see, suppose x stuck at 0 is detected 2 times, one with y equal to 1 and the other with y equal to 0, then this AND bridge fault of x y would have been detected by the second test. So, this is if this is detected 2 times, once with y equal to 1 and then y equal to 0, that means we can be sure that there is a bridging fault between x and y. So, for bridging fault detection, this may be one issue. If we are trying to get some confidence in the diagnosis process, okay, so if we are interested to get a diagnosis process, then we get some surety that okay, this particular fault has occurred, this particular defect has occurred. Then if a fault is detected many times by the applied test pattern, so we get confidence. The number of times a fault is detected gives us the surety that this particular fault has occurred in the circuit. So, that may be an issue. So, that way this N detect is used. Also, there may be some other points, like suppose we want to generate a test pattern set which consumes say less power. So, in that case also what we can do, possibly we can generate a redundant set of test patterns where every fault is detected by many patterns and then try to do a pick and choose. So, while doing this pick and choose, we pick up those vectors where the coverage is high, at the same time the power consumption will be low. So, taking these two into consideration, so we can have this pick and choose type of approach, and in that case also this N detect is going to help us, because it is going to give us an ATP of N patterns for every fault. Now, an ATPG can be very easily modified to work as an N detect ATPG. So, what is required is that you just change the fault dropping criteria. So, to conclude, so we have seen in this test pattern generation some theoretical foundation in terms of this Boolean difference and all that. We have seen combinational ATPG, sequential ATPG. We said that okay, under the scan conversion process, sequential ATPG it is rarely used, excepting some partial scan based circuits, but mostly it is combinational ATPG that is coming into picture. Then we have seen how to identify the untestable faults. So, there are this untestable fault identification can help this ATPG process, because it will be having less number of faults to work with. Then we have seen some simulation based techniques, and there are some hybrid ATPGs as well, which actually talks about this analog and digital combined ATPGs. Okay, so and this simulation, and also we have seen that simulation based ATPGs. So, they have been clubbed with this deterministic the initial pattern generation, the initial population generation. So, that is modified, so that that is also an hybrid ATPG. Then for delay testing, we have seen something, we have seen some techniques for delay fault generation, then delay fault test generation, then bridging fault testing also we have seen, then compaction, and how to compact a test set, then N detect, how to detect a fault N times. FSM testing is a part of sequential testing, so which we did not discuss in detail, but essentially one possibility is that you want to put the first we apply a sequence of patterns, so that this FSM goes to a particular state, and in that particular state we want to test a fault. So, then we apply some launch and capture pattern for testing that particular fault. So, the challenges that are remaining is the fast untestable fault identification, essential to remove large number of stuck-at bridge and delay faults. So, this is one of the very important issue, because with the increase in the complexity of the circuits, this number of faults in the circuit are increasing tremendously. So, if we can identify untestable faults early, then we do not put effort on doing this. That way, it can reduce the number of faults to be detected. So, this is becoming even more challenging. So, the identifying the untestable faults and doing it fast. Sequential ATPG is still an open research area, because of the fact that okay, this initialization itself is a problem. But anyway, with the introduction of these scan circuits and all that, so this sequential ATPG problem is addressed as a modified combinational ATPG problem, but still in some cases sequential ATPG will also be required. And other issues that are there is how to generate a test pattern set which will be which can reduce power consumption, which can reduce the temperature of the circuit. So those issues we will see in the later part of the course.